So we have ourselves a very beautiful, very lovely exam. This is Calc 2. Locally, we call this our Math 1660. And it's the exam 2, meaning we're going into the techniques of integration. That's right. We're practicing our integration. That means algebra, trigonometry, learning to rewrite things. It's going to be a lot of fun. Great vintage fall 2024. That was the start of multiple choice, so we have lots of interesting things ahead of us. Total of 10 problems. Of course, as always, if you want the credit, write your name and make sure we can read it. And, all right, off we go. Let's make sure we have plenty of time. So, into the multiple choice, number 1. We're asked to find the integral of sine squared of x cosine cubed of x. Now we say, okay. So this is one of those sines and cosine things going on. All right, what do we do? Well, there's a couple of cases, but the hopeful thing that we have is something with an odd power. And we look and we say, well, 2 is even, 3 is odd. Odd power, there we go. So no worries, we say. What we're going to do here is we're going to pull off one of our cosines. Now, what we're doing here is we're setting ourselves up. This cosine is going to become a du. That's the whole game. And so I say, okay, what does that mean? Well, we need to find something to substitute, so we're going to make everything else in terms of sine. Derivative of sine being cosine. And so I say, okay, well, is everything currently in terms of sine? Sine squared? Nice. Cosine squared? But we have that cool fact that says cosine squared plus sine squared equals 1. Now, what it really tells us is that if we have a cosine squared, we can swap it for a sine squared. Well, technically, it becomes 1 minus sine squared. And similarly, if we have a sine squared, we can swap it for a cosine squared. So we say, I'll swap out. And by the way, that's why we take advantage of the oddness, because when we pull off one of our cosines, we have an odd, becomes even. All right, so this becomes 1 minus sine squared x. And so, all right, great, beautiful. And now we're ready. We're ready. So here we go. Off to the races. And we're going to make a substitution. We've been setting ourselves up for a substitution. U equals sine of x. And then du equals cosine of x dx, right? That was our whole game, right? We were basing it off of a substitution. So it's u squared, 1 minus u squared du. And all right, well, that's the integral of u squared minus u to the 4th. And all right, 1/3 u cubed minus 1/5 u to the 5th plus c. And now we're almost there. We got to go back to x. U is sine. All right, so we have 1/3 sine cubed of x minus 1/5 sine to the 5th of x plus c. And do we have that as an option? We do. B. Nice. All right, life is good. Now, before we move on, I should have said, well, we were in the case where one of them was odd. If one of them is odd, pull it off to the end, and then we do a trade. If they had both been even, power reduction. So that's the two cases, really. Now, I said 3 originally because you pull off a sine, pull off a cosine, or power reduction. So, all right, cool. By the way, we knew it wasn't going to be the secants. So if you can eliminate a couple of choices, do it. It really helps. It really helps. Okay, well, we got to keep going. We could spend all day talking about some of these problems, but focus, right? Focus. Number 2. Choose the correct form of the partial fractions decomposition of x plus 3 over x minus 1 times x plus 2 squared times x squared plus x plus 1. All right. Now, x squared plus x plus 1 is what we call an irreducible quadratic, meaning we can't really factor it further. So before we start, let's just say, can we eliminate any options? Well, here's a good sort of quality check when you're doing partial fractions. Count the degree downstairs. And here, because we have a lot of stuff multiplying, we just add up. We'd have 1, 2, 3, because it's squared, 4, 5. Degree 5, right? Okay, now what does that tell us? It means in our partial fraction decomposition, we got to solve for 5 unknowns. So we need an A, B, C, D, E. And, okay, A goes through A through E. B, nope, not enough. Can't be B. C, nope, only has A through C. D, okay, possible. E, A through F. Nope, can't work. So it's none of those. All right, so we've already reduced it down to a 50-50 chance. And now we say, okay, well, what is it? Well, the way we do it is we build off of the individual pieces. So we say, okay, x minus 1, it better have an a over x minus 1. All right. Now, for x plus 2 squared, what do? Well, because you have that square, you have to build up. Okay, so that says we're going to have something over x plus 2 and something over x plus 2 squared. Now, some people say, instead of building up, they say moving down. But the punchline here is we have to have like one term for each power. And now this last term, that x squared plus x plus 1, well, there's only one of these, but because it's an irreducible quadratic, we have to have 2 terms upstairs. And if you look, that says the answer is D. Now, before we leave this one, I do have to say, A is kind of right. You know, you might say, well, wait, it's not in the same form. But it turns out they're equivalent after manipulation. But we tend to say this one is the way that we teach it. And so unfortunately, you really need to know the way that we teach it. And I know this is not a great answer. You're like, come on, give me a break. If I had guessed A, I should get something, right? I kind of sympathize with you if you had guessed A. And to be honest with you, if you had guessed A, you would have been able to solve for A, B, C, D, E uniquely, and you would have had a really great decomposition. All right, so anyways, on to number 3. Use Simpson's rule to estimate the value of the integral from 0 to 2 of 2x squared plus 3dx using n equals 4 subintervals. Okay, so Simpson's rule, now the way I remember that is you say, well, take the width, divide by 3, and then you have these coefficients, 1, 4, 2, 4, 1. All right, you're going up and down. And, all right, well, how do we use it? Okay, so if we were to do this problem the way it was asked, we'll do it again. We'll do it twice. This problem's so nice, we'll do it twice. Okay, so we're going 0 up to 2, and we're going to cut it into 4 equal parts. So cut, cut, cut. So, and that means we're going in step sizes of a half. And now what we need to do is we think of this is our function, our f of x, and we evaluate. Okay, so we plug in 0. 2 times 0 squared plus 3, 3. Plug in a half. 2 times a half squared, well, that's a half. Plus 3, well, we can write that as 7 halves. 2 times 1 squared plus 3, well, that's 2 plus 3, that's 5. 2 times 3 halves squared, all right, that's 2 times 9 quarters, it's 9 halves, plus 3, that's 6 halves, that's 15 halves. 2 times 2 squared is 8, plus 3 makes 11. Now, the delta x, that's this length, and that's a half. It's the width of one of these intervals. So we're going to take delta x over 3, 1/3 of 1/2 makes 1 over 6. And now 1 times 3 plus 4 times 7 halves plus 2 times 5 plus 4 times 15 halves plus 1 times 11. Right? 1, 4, 2, 4, 1. Okay, well, all right, we do math. Well, of course, we always do math. And that's 3. 2 goes into 4, so it's really like 2 times 7 making 14. 2 times 5 makes 10. 2 goes into 4, so that makes 2 times 15 makes 30. And 1 times 11 is 11. Well, here we can go. We got 40. And here, the rest of it, that's 25 plus 3 is 28. So that would make 68 times 1 6. And, well, they both have factors of 2. So that would be 1/3 times 34. All right. Good. Good. And that's the answer, right? Good. Now, I said this problem was so nice. We're doing it twice. So we're doing it twice. Okay, here we go. Round number 2. This is going to feel like we're cheating because we kind of are, but we're going to do it. What kind of function are we integrating? It's a quadratic. Quadratic, you say. Quadratic. What does that have to do with anything? Simpson's rule estimates using a quadratic, right? It's built off of parabolas. And so anytime you integrate a quadratic using Simpson's rule, there's no error. In fact, even if you integrate a cubic using Simpson's rule, there's no error. So what's going to be the value using Simpson's rule? All we have to do is integrate because there's no error. Literally, Simpson's rule will give you the exact value when you integrate a quadratic. So we say, well, okay, that's 2/3 x cubed plus 3x, and evaluate from 0 to 2. Plug in 0, you get 0. Plug in 2. 2/3 times 2 cubed, that's, 2 times 8 makes 16/3. And then you have 6. Well, okay, 6 is 18/3. Add those together, you get 34/3. And there's the answer. If you saw that, you are doing awesome. If you didn't see it, well, we still could have done it the other way. And so I just wanted to point that out. One of these, I wonder if they meant to do that. I don't know. I didn't write this test. I don't know. And probably if they saw it, they're like, oh, God, cheat. But you'd still get full credit, right? Because multiple choice. You don't check your work. Okay, number 4. Come on. Focus. We got a lot of problems to do. Suppose you are using the Simpson's rule with n equals 10 to estimate the value of this integral 0 to 1, 3x to the 4th plus sine pi x dx. Bound the error of this estimate using, and they give us the error formula, where this quantity m is the bound for the 4th derivative. And you look at these answers and you say, well, my goodness, they all look the same downstairs. Look at these downstairs, identical. And if you look at that, that's really 180 times 10 to the 4th. Okay, so great. That checks off. Now what about this b minus a to the 5th? Well, you look at your bounds are 0 and 1. So b minus a is 1. 1 to the 5th is 1. So what is this problem about? What is it you actually have to solve for? Good question, my friend. This problem is about m. Once you find m, you're done. And so these are your candidates for m. And so that's what you're looking at. And you can almost look at it and kind of guess what it is, but we're going to go ahead and work it out. No guessing. We're going to be professionals here. All right, so here we go. Our function, that's what we're trying to approximate. So we have f of x is 3x to the 4th plus sine of pi x. All right, start taking derivatives. 12x cubed pi cosine pi x. Second derivative, that's the derivative there. I know that the prime doesn't show up very much. Second derivative, 36x squared plus, actually it's going to be minus pi squared sine pi x. And where's this pi coming from? Chain rule. Chain rule. It's an awesome rule. It's a chain rule. So, third derivative, 72x minus, again, another pi comes out, pi cubed cosine pi x. And our fourth derivative, okay, 72, and derivative cosine will be sine. Now, what do? It's not about saying, oh, what is it at 0? What is it at 1? It's not about the values at the endpoints. It's about how big can you get? And we say, well, 72 can get 72 big. And so, well, those don't have 72 so forget about it. And what about this part? Well, here's where we use what we know about sine. And there's a lot we know about sine. And so it can be kind of like, but what part of sine do we care about? Well, we're trying to say, how big can it get? How big can sine get? Well, sine is an oscillating function, and it goes between -1 and +1. So this part is bounded, but can't get bigger or smaller than 1. So the biggest this whole thing can get is determined by how big this can get, and that can get as big as 1. So we have that the size of this is going to be less than or equal to 72 plus pi to the 4th. And that would be, happens at x equals 1/2. And that's when we maximize it out. So we're looking for, remember this was our m, that has to be one of these values. It's e. All right. Good. Awesome. Making progress. We're coming right along. We're almost halfway through the test, right? Because there's only 10 questions. We're on number 5. And, well, okay, so we're in multiple choice. But we're almost done with that. Come on. Focus. Okay. The integral, 0 to root 5, x to the 4th over root 5 plus x squared dx can be rewritten as which of the following? All right. And they have a bunch of options. And, oh my gosh, that d is so tempting, isn't it? Root 5 plus x squared, square root of 5 plus square root of x squared. Doesn't that work? No. This is trying, they call it, mathematicians have this idea called the freshman's dream. Like, oh, wouldn't it be nice if square roots worked that nicely? No, that is not how square roots work. Oh, no, don't be tempted. Don't be tempted. Okay, so that's why they threw that one in there. All right, but I'm guessing, because this does not look like x to the 4th and x cubed. So, yeah, that one's just hopeless. You got x's downstairs, forget it, hopeless. So there's tangents and secants. Those are the ones we should be focusing on. And we suspect that we have a trig sub coming, because what do we see? A square root. And when we see square roots, especially on this test, we're like, trig sub. Okay, so we're channeling our inner trig sub. Trig sub. Okay. Well, if we think about what's going on, well, what do we want? We have number plus function squared. And so we really should think of this as square root of 5 squared plus x squared, because we really want it number squared plus function squared. Now, when it's in this form, the substitution is u equals a tangent theta. So for us, u is x, so x equals a is square root of 5. Square root of 5 tangent theta. Okay, cool beans. Now, we have to do some work. We say, well, what's dx become? Derivative of tangent, secant squared theta d theta. And the other thing is, what happens to the square root of 5 plus x squared? Well, it's going to become something nice. It's going to become the square root of 5 plus 5 tangent squared. And you can pull off a 5 on the inside, so the square root of 5 times 1 plus tangent squared. Well, that's the square root of 5 secant squared, which is square root of 5 secant. All right, so now let's see what we have. So we have an integral. We have x to the 4th, square root of 5 tangent theta to the 4th. We have a dx, square root of 5 secant squared d theta. And then we have the downstairs, square root of 5 times secant theta. And at this point we say, well, okay, what's there? And we can get a square root of 5 to cancel. We can get a secant to cancel. And we have square root of 5 to the fourth makes 25. So we have 25 integral tangent to the fourth theta, secant theta, d theta. There's only one of those options. Ha! Whew! Good. That makes it a lot easier. Okay. So that says our answer is C. Good, good. Now you might say, are any of these others very tempting answers? And they are. If you had forgotten this square root of 5 secant squared theta, then the answer would have been B. And by the way, what didn't we do? We didn't update the bounds. But we didn't update the bounds because we didn't need to. We saw the right form. Let's suppose we did. Let's suppose we did. And if we were to update the bounds, we say, well, we have x bounds originally, and plug in 0. When does 0 equal square root of 5 tangent theta? And the answer is at 0. Okay, that checks out. Now, the other one is a little bit more interesting, square root of 5. So we plug in square root of 5. Square root of 5 equals square root of 5 tangent theta. That says tangent theta equals 1, and that is at pi fourths, which, okay, that does match the upper bound. All right, and you'll notice that here, they said, forgot to change your bounds. So we make sure, if you have bounds, update them. Sometimes they'll be similar right up to the bounds. But, all right, that's number 5. Last multiple choice question. Which of the following integrals correctly evaluates the improper integral? Okay, so it's an improper integral, and we know it because it says improper. Nice. All right, so we say, where's the problem? Well, there's no problem at the endpoints because those are numbers. They're not infinity or minus infinity. So there's got to be a problem in between. So we say, okay, well, looking at what we have, we see a negative exponent. That means we're dividing possibly by 0 because negative means downstairs. And we say, well, what could make x minus 2 be 0? 2. All right, cool. So we say to ourselves, cool. So we have negative 5 to 5. So what we want to do is we want to go from negative 5 up to something a little bit below 2. And then we want to go from something a little bit above 2 up to 5. And, all right, so 2. We want to get close to 2. Notice here, this says get close to 0. No, we don't want to get close to 0. This one also says get close to 0. Nope. This one says you're getting close to 5. Hopeless. All right, so it's down to B or C. What's the difference between B or C? And you might say, my goodness, they look very similar, especially at the resolution you have, Steve. Can you even spot a difference? Well, there is a very tiny, subtle difference. And it's this little bit here. What are these? There's a little minus there, a little plus there. These are one-sided limits. And that's important because we don't want to go from negative 5 and above 2 and then go down. We want to go from negative 5 to below 2 and go up. So here, from negative 5, we want to have it go to 2 from below, 2 minus. And so here, between 2 and 5, we want it to go from 2 from above. All right, so that's 2 plus. And so you really, whenever you have limits in these improper integrals, they're truly one-sided limits. One side, and so you want the one-sided version. So the answer is C. If you put B, I feel for you. Oh my gosh, it's super, super tempting, and but you have to be really careful with these improper integrals. They can throw you for a loop. All right, well, that takes us out of the part of multiple choice on to section 2, workout. So now we've got the long answer problems. Number 7. Find the volume when the region 0 less than or equal to y less than or equal to 2 times 4 minus x squared to a quarter. And x goes 0 to root 2. Now, they didn't mark things for us, but I'm going to guess this is root 2. And here's the curve y equals 2 times 4 minus x squared to the 1/4. All right, so anyways, we want to find the volume when this is revolved around the x-axis. And they gave us a nice little arrow around. Okay, so we start thinking, what's the technique? We know it's volume, because it says volume, and we have two methods, right? We have shell method, and we have the disk method. I say disk because I don't think this one will be holy. There's no holes here. And how do you know? Because it could be either. There are applications of what we've learned which might use one or the other. So, looking at what we have, I say, well, this is a function of x. True story. And we say, okay, well, if it's a function of x, let's slice like we would for x. And so, in other words, we're going to have vertical slicing. And if we spin that, the question is, what shape gets formed? And the answer is, this is forming a disk. So we want to use the disk method. Okay, so now that we know which method we want, that's going to help us focus our energy. So we say to ourselves, because of course we have lots of energy, as we always do when we're taking a test, how do we use the disk method? Well, volume is the integral a to b pi, and since there's no hole, just a single big radius, quantity squared, and a width. All right, good. Now for us, we start thinking about, what do we know? Well, we have a and b given. 0 and root 2. And okay, so 0 to root 2 pi. What's the radius? Well, it's that part. Okay, so that's going to be 2, 4 minus x squared to the 1/4 quantity squared. And what's the width? Well, the width is just a small little change. In our case, it's dx. So width is dx or dy, depending upon how you integrate. All right, well, let's clean this up, and let's see what we have. The pi can come out. 2 squared is 4. Don't forget the square of the 2. It's so easy to forget when you're squaring a bunch of stuff. Sometimes you just square the last thing. Got to square the whole thing. So that's 4 pi, and so might as well pull that out as a constant in front. And integral from 0 to root 2, 4 minus x squared to the half. All right, so there we go. Now, you could do the rest of what we're about to do with geometrical reasoning, but because it's a calculus test, I think they want us to do calculus, so we're just going to do calculus to do this. All right, so here we go. Calculus. Channeling our inner calculus. What does our inner calculus tell us to do? Well, we see a square root. That's what 1/2 means. We see a square root. We look and say, well, what kind of things do we have? Well, it's something squared minus function. A number squared, right? Number squared minus function squared. We say, oh, okay. We have a squared minus x squared. U squared. And so in our case, a is 2. 2 squared is 4 minus x squared. Now, normally this would become u equals a sine theta. So for us, our substitution is x equals 2 sine theta. Now we start making some notes. We say dx, well, that's 2 cosine theta d theta. And the other thing we should note is the square root of 4 minus x squared. That becomes square root of 4 minus 4 sine squared. You can pull out a 4. And so you have 1 minus sine squared. Oh my goodness, you probably don't usually write this all down, but in the interest of being thorough, it becomes 2 cosine theta. So the punchline is we can replace the square root of 4 minus x squared. We can replace the dx. What about the bounds? Oh, yes, of course. The bounds, I'm so glad you asked about those because we should pay attention to the bounds. These are x bounds. We don't want x bounds, we want to go to theta bounds. So let's do our bounds really quickly. And okay, so x equals 0. What happens? We plug in, we get 0 equals 2 sine theta, or that says sine of theta equals 0, which says theta equals 0. Okay, so that's going to be one of our bounds. What about the other bound? X equals root 2. We get, plug in root 2. Root 2 equals 2 sine theta. Then we get sine of theta equals root 2 over 2. And we remember, or we look it up, whichever way we do it, and say, hey, that's a pretty convenient angle, pi quarters, pi fourths, 45 degrees. All right, cool. And so, with all of our work that we've put in, we're now ready to say, what's our integral? 4 pi, new bounds, 0, pi over 4. And then, this square root of 4 minus x squared, 2 cosine theta. The dx, 2 cosine theta again. They really love that 2 cosine theta. And all right, we're in business. So we've transformed our algebra into trig. And that's the point of view of this trig substitution. It's saying, hey, let's transform one type of problem into another type of problem. And that lets us make progress. Okay, well, what can we do? Well, certainly we can pull out the 2's. And so if we pull out the 2's in front, that gets us to 16 pi. And we have the integral of 0 to pi over 4. And then we have cosine squared. Okay, what do we do with that cosine squared? See, this is a case when we have sines and cosines, all the powers are even. We have ways to deal with that, and that is power reduction. So we say, hey, cosine squared, that's 1/2, 1 plus cosine 2 theta. All right, so we're going to replace this cosine squared with this 1/2, 1 plus cosine 2 theta. And we'll go ahead, pull the 1/2 out. 16 pi times 1/2 makes 8 pi. Then we have integral of 0 to pi over 4. 1 plus cosine 2 theta. All right, we're doing great. We're almost done because now we're pretty comfortable. These are things we can integrate, and we like it when we get things we can integrate. So this is 8 pi. We have theta plus 1/2 sine 2 theta, right? Because the integral of cosine is sine, but because of the 2 on the inside, we have to compensate. So we divide by 2 in front. Evaluate 0 to pi over 4. Now, plug in 0. 0, 0. Nice! It's always good when the 0 term vanishes. Gotta check. Sometimes it doesn't, but when it does, celebrate. Okay, plug in pi over 4. All right, so what do we have? We have 8 pi times pi over 4 plus 1/2. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. And let's go ahead, last step, distribute it out, because it looks like if you multiply in, the fractions will go away. 8 divided by 4 makes 2, so 2 pi squared. 8 divided by 2 is 4, plus 4 pi, and there we go. All right, that was our first workout problem. Whew, did you feel like you got a good workout? Well, good news, 3 more. All right, number 8. Find the integral pi over 2 to pi of square root of 1 plus sine x dx. Now it'd be like, how do we do that? Man, it would be nice if we had a hint. Oh, they gave us a hint? Oh, they were feeling pretty nice. Okay, so let's use their hint. Multiply by the conjugate expression. And they might say, what do you mean by the conjugate expression? Well, the conjugate expression is saying, hey, take the plus, change it to a minus, right? A plus B, conjugate A minus B. If you have A minus B, conjugate it's A plus B. And so why do that? Well, 1 plus sign can't do much with. But if you multiply by the conjugate, it becomes 1 minus sine squared. Word! That you can do something with. All right, so we have an idea. All right, so here we go. Integral pi over 2 to pi. We have the square root of, and I'm going to do a lot of work inside the square root for a second, because when you multiply by the conjugate, you always got to be really careful, because multiplying can change things. Changing things gives us a different problem, which has a different answer. So we got to be careful how we multiply so we don't change. So the way we make sure that when we multiply and we don't change is we multiply by the 1. We are after the 1. So what that means is that we're going to multiply by something which doesn't change our answer. So for us, that's going to be 1 minus sine x over 1 minus sine x. And, okay, dx. So I'm multiplying on the inside, and lo and behold, I don't have any issues here. Life is good. Life is good. Okay, well, what does this become? It becomes integral pi halves to pi of, now upstairs, we have the square root 1 minus sine squared of x, and downstairs we have 1 minus sine x. And in the moment, you might say, you made it worse. But hold on, we're not done yet. We're going to go further. All right, well, this becomes what? The key here, the whole reason we did conjugation is we wanted to get that 1 minus sine squared, because this becomes cosine squared. Ah, nice. Nice. Ah, that's nice, because we have a square and a square root, and we can do stuff with it. Now, we're going to go through, and there's kind of some interesting things going on here that I don't think they intended on this problem. So I'm going to have some commentary here. And I did not write this problem. I didn't write this test, but do you notice that we started with a perfectly fine integral? This integral, a little bit dicey at pi halves, right? Because you got 0 over 0. Is it improper? Maybe. But here's the good news. It's not improper because it has the same value. So there's no blow up, but it kind of feels weird. But here's the part that's going to probably really annoy people. Let's talk about something. We're going to take the square root of cosine squared x. All right, what is it? Now, I know you're sitting there, you're like, Steve, it's cosine of x. What are you saying? Come on, don't play with me, Steve. Don't play your game, Steve. But I'm going to play this game because it's a fun game. Is this the right thing? Will we replace the square root of cosine squared x? Because you can think of this as the square root of cosine squared x upstairs. Oh, excuse me. My voice is going because I'm so excited. And the square root of 1 minus sine x downstairs. So, is this what we put in? And why not? It's not. And that's annoying. So let's explain what's going on. When we take the square root of a square, you don't actually get the function back quite. You get the absolute value of the function back. And now they did something kind of like, look at our range. Pi halves to pi. Now, between pi halves and pi, what's true about cosine? cosine is negative. So what does that tell us? Well, if cosine is negative, what's true about the absolute value of cosine of x? Well, it's going to be negative cosine of x for our pi halves less than or equal to x less than or equal to pi. So here we go. Being ever so careful, because we get the following. This is integral pi halves to pi of negative cosine of x over the square root 1 minus sine x dx. Now, you might be wondering, what if we forgot that negative? Well, the answer is everything else would proceed as normal. Your answer would have ended up being negative. And if you were like, oh, cool, got a negative, whatever, and moved on, you would have lost a point. Maybe two. Because we started with something which was definitely not negative. And so, yeah, this matters. This matters. And why did they choose to do that? I don't know. But they did. They made choices. That's all right. We'll keep working on it. All right, 1 minus sine x. Here's where everything that we've done pays off. Because initially, there's not really much we can do. If we try a substitution, the derivative of sine is not floating around. But now, the derivative of sine is. It's up there. So we say, okay, well, let's let u equal 1 minus sine x. It's what's on the inside. And we say, well, what is our du? And the derivative of du, well, all right, derivative, no, look, all right, I'm tempted to look there. No, look here, come on. Negative derivative of sine is cosine x dx. Like, nice. Okay, so we have integral of du over square root of u. Now, our bounds. Plug in pi over 2. 1 minus sine of pi over 2. So at pi over 2, we have 1 minus sine pi over 2, which is 1 minus 1, which is 0. So we're going to put in 0. And at pi, we have 1 minus sine pi. That's 1 minus 0, which is 1. All right, 0 to 1, du over square root of u. The end is in sight. Now, we'll make some notes here. This is improper, but let's just proceed with caution. Keeping in the back of our minds that this is improper, we'll integrate, and we won't worry about limits unless we truly need them. Now, you're probably saying, but how do we know if we truly need our limits? Excuse me. Well, if you have something where you can't figure it out. Okay, so this is integral 0 to 1, u to the minus a half du. Add 1. You have u to the 1 half. We also then have to divide by half, which means multiply by 2. So 2u to the 1 half evaluated from 0 to 1. And now we say, all right, 0 was a problem. Is 0 a problem here? And if the answer is no, it's like, great, just plug it in, life is good. Because it's not an issue. If it's a problem, then you take a limit, but here there's no issue. All right, so you plug in 0, you get 0. Plug in 1, you get 1. That seems like after all of that great excitement, you're like, man, Steve, you're just like, at this point, not super enthusiastic. No. We're having a great time. We're all enjoying ourselves, right? I hope you're having a good time. And there we go. 2. All right. What an interesting journey. Of course, do we have to worry about it being proper? I don't think so. Otherwise, they would have told us. And I think the hard part about this one is recognizing where that minus comes from. And, what an interesting choice to put that on. All right, but let's move on. We are happy people. Number 9. Find the integral 2x squared minus 7x minus 3 divided by x minus 2 times 2x squared plus 1. Cool. So what do we have? Polynomial upstairs. Polynomial downstairs. It's a rational function. Okay, so when you have rational functions, the procedure is partial fractions. We're going to channel our partial fractions. Now, step what I call 0. Do we need long division? Well, downstairs, if you were to multiply it out, you'd have degree 3. Upstairs, we have degree 2. Downstairs is bigger degree. Good. Don't need to worry about long division. All right, next step. Do we need to factor? Ha! They were nice. They factored it for us. And so we're like, wow, man, they're taking a lot of the hard stuff and doing it already. Now we get to the work. So we're going to pull this off to the side. And so most of the work of partial fractions is partial fractions, which is algebra. That's happening over on the side. The integration, which we'll get to later, usually isn't too bad. Let's hope that holds true here. Okay, all right, here we go. So we have 2x squared minus 7x minus 3 divided by x minus 2, 2x squared plus 1. Well, that's going to be, go term by term. There's our first term, x minus 2. It's linear, so there's only one of them, and put a single constant. Next term, 2x squared plus 1, quadratic, and it's irreducible quadratic, so there's going to be something, 2x squared plus 1, and upstairs we need 2 pieces, cx plus d. All right, so that's our form. Now, sanity check, count the numbers of unknowns, and I don't know why I skipped b. Why did I do that? I don't know. Okay, whatever. We have 3 unknowns. Sorry about that. I have nothing against b. B is wonderful. Some of my best friends have B's. But all right. So there's 3 unknowns, degree 3, good sanity check. This is pretty reasonable. It's probably right. Clear your denominator. Now remember, when you're clearing your denominator, use this to multiply. In other words, what was your original denominator? You're multiplying it through by everything. So when we clear our denominator, and so we're timesing by, times by x minus 2 and 2x squared plus 1. Sorry, I ran out of space there. What will happen, we get that 2x squared minus 7x minus 3. The first place, the x minus 2's cancel, so that's a times 2x squared plus 1, plus the second case, the 2x squared plus 1 cancels, so it's cx plus d times x minus 2. Now, at this point, there's a couple of choices. Ultimately, we have to solve for our unknowns, a, c, and d. What we have to do is be careful. And say, okay, well, how do we do that? We can make good choices. In other words, pick values for x, or we can expand coefficients and compare. Now, I always recommend make good choices first. If you can do that, that can help. And even if you ultimately expand later on, if you can make a few good choices early, life is good. So, what's a nice choice? Well, I claim 2 is nice because 2 will zero something out. We make good choices by saying, is there something which makes a 0? So we see something. And if you see something, do something. So we say, all right, our good choice is x equals 2. So we have to plug it in. 2 times 4 is 8, minus 14 minus 3 equals a. 2 times 4 is 8 plus 1. And then you get 2c plus d times 0. Okay, so that's at least some good news there. All right, so let's see what we have. Okay, 8 minus 14 minus 3. It's 8 minus 17. And that's negative 9 equals a times 9. And so a is negative 1. Okay, good. So we can even just mark it up here. This is negative 1. All right, good. And on a side note, I keep mentioning this, one of the most common mistakes that people make with partial fractions is they forget to put the right number in the right place. So they find the numbers, but then they sort of jumble them up, or they find the numbers and they forget to put them in there. So make sure once you have a number, make sure you put it in the right place. Okay, all right, come on. Got to focus, right? We've already used up 2/3 of our time, and we still have a lot of problem left. Okay, now, are there any other good choices? Well, actually there is. See how we have cx? If you put in x equals 0, that part goes away. But you might say, but what about the a? We know a. So let's plug in x equals 0. Let's see what we get. Well, 0, 0, negative 3. Cool, so negative 3 equals a times 1, but we know a, so that's minus 1 plus, and then we get c times 0, which is gone, plus d, so plus d, times minus 1 times minus 2. So times negative 3, right? Yeah, that sounds right. Okay, good. So we have minus 3 equals minus 1 plus d. Whoops. I plug in 0, Steve. Come on. Minus 2. Minus 2. You gotta check. Gotta check. Small mistakes will throw you off. And I was kind of like skeptical because I was seeing that I was going to turn into an unpleasant fraction. Our calculus teachers love us enough. They're not going to give us unpleasant fractions. Come on. They love us. They're good people. They're good people with big hearts who take care of us. All right, so we can add 1 to both sides. We get minus 2 equals minus 2d. And we say, oh, well, that's good. D equals 1. So we've solved for A. We solved for D. That just means one more to solve for. And you might say, joke's on you, Steve. You've run out of good choices. But I don't really care at this point. I just need one more. I can just plug in any convenient number. How about 1? Sure, why not? So here we go. 2 minus 7 minus 3 is equal to A, which is negative 1. 2 plus 1 is 3. Plus, we don't know C, so it's C plus D, which becomes C plus 1, because we do know D equals 1. And 1 minus 2 is a minus 1. Okay, so 2 minus 7 minus 3, that's really 2 minus 10. That's negative 8 equals, we have a minus C, and now there's a minus 3 and a minus 1. And we put those together, it's negative 4. Well, everything's negative. Come on, we're optimists. Plus this. So 8 equals C plus 4, so C equals 4. All right, now we didn't update. D equals 1, and C equals 4. All right, so all of our work so far has been to say this expression, 2x squared minus 7x minus 3, divided by x minus 2 times 2x squared plus 1, is negative 1 over x minus 2 plus 4x plus 1 over 2x squared plus 1. All right. Well, now we return to our regularly scheduled integral. We can say this is the same as the integral. We just copy minus 1 over x minus 2 plus 4x plus 1 over 2x squared plus 1 dx. All right. Now, the first part, looking good. That's going to be pretty stressless. 2x squared plus 1, you have a 4x plus 1 on top. And, well, if you set u equals 2x squared plus 1, the derivative of that is 4x, so that's kind of good. But then you have the plus 1. So it's not quite enough to say u equals 2x squared plus 1 and du is the top, because it's not true. But what we can do is take advantage of the nice plus sign that we have upstairs. All right, so let's do that. So what do we have? I'm going to write this as negative 1 times 1 over x minus 2 plus 4x over 2x squared plus 1 plus 1 over 2x squared plus 1 and dx. Okay, good. Now, this first integral, we can do that, no problem. 1 over x minus something, 1 over x plus something, that's a log. So we have minus a log x minus 2. Okay, so that's first one, great. 4x over 2x squared plus 1. If you let u equal 2x squared plus 1, du equals 4x dx. So it really becomes 1 over u du, right? Because you have derivative upstairs, function downstairs. That's a log u, which is log of 2x squared plus 1. Okay, so that term, great. That term, okay. We're going to have to spend a minute here. All right, so let's write down what we have. We have minus log x minus 2 plus log 2x squared plus 1 and something plus c. All right. We still have to do that integral. Let's, it sounds like I'm going, ugh. I kind of am a little bit because as much as I love an arctangent, and I can feel an arctangent coming, I also sense like, oh, these are not nice numbers. But let's go ahead and do it. Okay, so why do I feel an arctangent coming? Well, because what we have here is like, it looks a lot like, you know, if you kind of squinted and you didn't see that 2, it looks a lot like 1 over x squared plus 1. Like, oh yeah, that does feel like arctangent. So how do we integrate this type of thing? Well, one way to do it is to memorize a formula that you probably will only use 4 times in your life. Or you say, well, let's rederive it. Here we go, we're going to rederive it. And the way we can do it is trig substitution. And I know you're thinking, like, again? Haven't we done enough trig substitution, Steve? Can one ever truly do enough trig substitution? It's one of the great philosophical questions of life. And the answer is yes, one can do enough trig substitution. All right, so let's think of this. We want to write this as u squared plus a squared. Well, the a squared, that's pretty easy. That's 1 squared. How do we write 2 times x squared as a square? Well, it's square root of 2x quantity squared. So there's a square root of 2 involved. So if our substitution is u equals a tangent theta, this has square root of 2x should be equal to tangent theta. A is 1, and u is square root of 2x. Well, that tells us then that square root of 2 dx is secant squared theta d theta. And we can move that square root of 2 across, or dx is 1 over square root of 2 secant squared theta d theta. Now, what happens to this 2x squared plus 1? Well, 2x squared plus 1 becomes, well, the square root of 2x squared is tangent squared plus 1, so that becomes secant squared. So, with this substitution, we have 1 over secant squared. That's our first part. The dx is 1 over square root of 2 secant squared d theta. The secant squareds cancel, so this becomes the integral 1 over square root of 2 d theta. which is 1 over square root of 2 theta. Toss on a constant just because we're being super careful. And now you say, well, hey, how do you find theta? Tangent of theta is square root of 2 of x. So theta is arctangent of square root of 2x. So we end up with 1 over square root of 2 arctangent square root of 2x plus c. And that's what goes there. All right. And so, yeah, if you can remember that, that's great. And if you can't, we can always rederive. So 1 over square root of 2 arctan of square root of 2x. Arctangent is not so surprising. The fact that we have a square root of 2 maybe is a little bit surprising, and we have to make sure we're very careful and that we account for that. All right, well, all good things have to come to an end. That brings us to our last problem. Man, it feels like we'd only just begun to solve. All right, let's not get too caught up in song. Compute the following indefinite integral. That's not an indefinite integral. That's really strange. Compute the following definite integral. Indefinite is if there's no bounds. Oh, you know what? I think what they meant to say, compute the following improper integral. Okay, typo. That's okay, come on. We'll give them a break. We're kind to our calculus professors just as they are kind to us, right? Right? Yeah. Let's do that. Let's be kind. So compute the following improper integral or explain why it does not exist. Be sure to show your work. Okay, so why did I call it improper? Well, it's definitely not indefinite because it has bounds. Indefinite means no bounds. Improper is something involving infinity. And I can't help but notice there's an infinity here. And so we have an infinity here. All right, so we need to deal with our infinity. Okay. And on a side note, this is technically not the first time we've seen an improper integral on this test, but here we're going to be extra careful and take our time. Maybe not take too much time because we only have, about 10 or so minutes left. Take a little bit of time. Enjoy the process. Enjoy the process. Okay, so how do we begin? Now, one strategy you can do is say, let's first do the indefinite integral, and then we'll come back and do the definite part. Okay, so I'm going to employ that strategy. So let's suppose we were asked to integrate the following. Integral of 7x e to the minus x over 3. Looking at this, I see that I have polynomial and exponential. So I have sort of two different types of functions blended together. That's a sign of doing integration by parts. Another sign to do integration by parts is, this is the last problem and we haven't done it yet, so we better do it, right? Okay, yeah, so there's multiple signs. But again, blending different types of functions, polynomial with exponential or polynomial with trig or, exponential with trig, those are signs that it's like, okay, integration by parts. And we say to ourselves, well, whether you integrate or differentiate an exponential, it's going to look exponential-ish. What do you want to do with the x? Take a derivative or integrate? We're probably a lot better off taking a derivative because by taking a derivative, it gets simpler. And our goal in all the things that we do, our goal is simplify, simplify, simplify until answer comes out. Okay, so with that in mind, we say we're going to let u be the 7x and the dv e to the minus x over 3. du becomes 7dx. And the integral of e to the minus x over 3, well, it's e to the minus, sorry, not the integral, the antiderivative, because that's dv. It's e to the minus x over 3, But then you got to account for that negative 1/3 upstairs. So you divide by negative 1/3, which means multiply by negative 3. All right, so we have uv. So that's minus 21x e to the minus x over 3. Okay, great. Minus the integral of v du. So minus the integral of minus 3 e to the minus x over 3 times 7 dx. Well, 2 wrongs make a right. 2 minuses make a plus. Actually, 2 wrongs don't make a right, but 2 minuses do make a plus. All right, so we have here minus 21x e to the minus x over 3. 3 times 7 can come out as a plus 21. And then the integral of e to the minus x over 3 is the same thing as what we did over here. So times another negative 3 e to the minus x over 3 plus c. Or if you like, minus 21x e to the minus x over 3 minus 63 e to the minus x over 3. Wow. Whew. What an expression. What an expression. Plus c. Okay. All right. Well, now let's jump back to our problem. Okay. Here we go. So we can now say, what's going on? Well, this integral is improper just because of that bound. There's no place else that's wrong. There's no minus infinity bound. There's no place where we're dividing by 0, so nothing's blowing up. Whew. Good news for us. So to deal with it, we say, well, we're going to do it by taking a limit as b goes to infinity. Now, when they really go out of their way to specify something's improper, put that limit in there because they're looking for it. If you leave it out, they'll be like, whoa, hey, why'd you leave it out? Better take off a point. So put that limit in. Put that limit in. All right, integral 0 up to b of this expression, 7x e to the minus x over 3. And now we say, hey, we know that integral, so we can do it. And in fact, we should have done this up here. Notice, what can you do? We can say this is the limit as b goes to infinity. Well, we can factor out a factor of negative 21. So let's go ahead and do that. We can factor out an e to the minus x over 3. We could do that. And when we factor those terms out, we're left with an x plus a 3. All right. And evaluate 0 to b. Okay. All right. Now, great. So this is our limit as b goes to infinity of, plug in the b, we have minus 21 e to the minus x over 3, e to the minus b over 3, times b plus 3. All right. Now that's plug in b, subtract, plug in 0, minus, here you get a minus 21 times 1 times 3. And, okay, minus minus makes a plus. And so this is 63. So this part at the end, that's not going to change. So we're just going to put it down front. So we really have 63 plus the limit as b goes to infinity and minus 21. Now here's the thing. What's happening here? This e to the minus b over 3, think about what's happening. All right. That's going to get small. B plus 3 is going to get big. Small times big is more work. More work, right? It's 0 times infinity. So we're going to set it up as a fraction. So the thing is, because we have this minus exponent, that says put that downstairs. B plus 3 over e to the b over 3. Now, what's going on? Well, currently this is going to infinity over infinity, right? We get a huge number, huge number. Infinity over infinity, more work. What's our favorite kind? Le Hopital, mon ami. We get to do Le Hopital again. Okay, so we have our 63. Plus, we have our limit. As b goes to infinity, we're doing a L'Hopital, so we mark it. Mark that you're doing L'Hopital. Indicate you have some sort of infinity or 0, 0. Make sure you show it because they're looking for it. You want to get the points. You want to get all the points. B is what we're taking limit of, so B is the variable. Well, the derivative of b plus 3 is 1. Downstairs, we have 1/3 e to the b over 3. Use the chain rule. Now what happens? The top is fixed. The bottom gets big. Number, -21, divided by something huge. This part goes to 0. So our answer is 63. Done. Whew! Now, I'm going to be honest. Between you and me, nobody else listening, just us. Let's talk. Real talk. This was kind of hard. I'll be honest with you. I think this was a challenging test. Partially because the numbers were a little bit hard. It could have been a little bit nicer. And it was long. It was long. I don't want you to get nervous, though. This was a test before. It's not the test you're going to face. Your test is your test. And it's something that you can do. So put in the work. You can do it. I believe in you. You're working hard. It's going to pay off. So don't panic. Go into that test. Breathe in. Breathe out. You can do it. Your calculus professors like you. I promise they really do. And they'll give you something that you're able to do. Thanks for coming. Thanks for putting in the work. And I hope you have a great test whenever that might be. And maybe let's meet up again and do this another time.